A solved game is a game whose outcome can be correctly predicted from any position, given that both players play perfectly. Games which have not been solved are said to be unsolved. Games for which only some positions have been solved are said to be partially solved. This article focuses on two-player games that have been solved. Overview. A two-player game can be solved on several levels. Ultra-weak prove whether the first player will win, lose, or draw from the initial position, given perfect play on both sides. This can be a non-constructive proof that need not actually determine any moves of the perfect play. Weak provide an algorithm that secures a win for one player, or a draw for either, against any possible moves by the opponent, from the beginning of the game. That is, produce at least one complete ideal game with proof that each move is optimal for the player making it. It does not necessarily mean a computer program using the solution will play optimally against an imperfect opponent. For example, the checkers program Chanook will never turn a drawn position into a losing position, but it might possibly turn a winning position into a drawn position because Chanook does not expect the opponent to play a move that will not win but could possibly lose, and so it does not analyze such moves completely. Strong provide an algorithm that can produce perfect play from any position, even if mistakes have already been made on one or both sides. Despite the name, of many game theorists believe that ultra-weak are the deepest, most interesting and valuable proofs. Ultra-weak proofs require a scholar to reason about the abstract properties of the game, and show how these properties lead to certain outcomes if perfect play is realized. By contrast, strong proofs often proceed by brute force, using a computer to exhaustively search a game tree to figure out what would happen if perfect play were realized. The resulting proof gives an optimal strategy for every possible position on the board. However, these proofs aren't as helpful in understanding deeper reasons why some games are solvable as a draw, and other, seemingly very similar games are solvable as a win. Given the rules of any two-person game with a finite number of positions, one can always trivially construct a min-max algorithm that would exhaustively traverse the game tree. However, since for many non-trivial games such an algorithm would require an infeasible amount of time to generate a move in a given position, a game is not considered to be solved weakly or strongly unless the algorithm can be run by existing hardware in a reasonable time. Many algorithms rely on a huge pre-generated database, and are effectively nothing more. As an example of a strong solution, the game of tic-tac-toe is solvable as a draw for both players with perfect play. Games like NIM also admit a rigorous analysis using combinatorial game theory. Whether a game is solved is not necessarily the same as whether it remains interesting for humans to play. Even a strongly solved game can still be interesting if its solution is too complex to be memorized. Conversely, a weakly solved game may lose its attraction if the winning strategy is simple enough to remember. An ultra-weak solution generally does not affect playability. Moreover, even if the game is not solved, it is possible that an algorithm yields a good approximate solution. For instance, an article in Science from January 2015 claims that their heads-up limit Texas Hold''em poker bot Cepheus guarantees that a human lifetime of play is not sufficient to establish with statistical significance that its strategy is not an exact solution. Perfect play. In game theory, perfect play is the behavior or strategy of a player that leads to the best possible outcome for that player regardless of the response by the opponent. Based on the rules of a game, every possible final position can be evaluated. By backward reasoning, one can recursively evaluate a non-final position as identical to that of the position that is one move away and best valued for the player whose move it is. Thus a transition between positions can never result in a better evaluation for the moving player, and a perfect move in a position would be a transition between positions that are equally evaluated. As an example, a perfect player in a drawn position would always get a draw or win, never a loss. If there are multiple options with the same outcome, perfect play is sometimes considered the fastest method leading to a good result, or the slowest method leading to a bad result. Perfect play can be generalized to non-perfect information games, as the strategy that would guarantee the highest minimal expected outcome regardless of the strategy of the opponent. As an example, the perfect strategy for rock, paper, scissors would be to randomly choose each of the options with equal probability. The disadvantage in this example is that this strategy will never exploit non-optimal strategies of the opponent. So the expected outcome of this strategy versus any strategy will always be equal to the minimal expected outcome. Although the optimal strategy of a game may not be known, a game-playing computer might still benefit from solutions of the game from certain endgame positions, which will allow it to play perfectly after some point in the game. Computer chess programs are well known for doing this. Solved games. Owari, the variant of Owari allowing game-ending Grand Slams, was strongly solved by Henri Bal and John Romain at the Vrije Universiteit in Amsterdam, Netherlands. Either player can force the game into a draw. Note that the Spanish Owari master Victor Bautista Iroca claimed on his former homepage mancala.org that the Owari oracle had several flaws in the endgame and that it therefore can be doubted that the solution of Bal and Romain is valid. However, both sites have been taken off the internet and no further research appears to be possible. This reveals a major problem. Most research done in solving games is not fully peer-reviewed. Minor mistakes in the programming, which nevertheless can give quite different results, will usually go unnoticed. Checkers. See Drafts. English. Chopsticks. The second player can always force a win. Connect for solved first by James E. Allen, and independently by Victor Alice. First player can force a win. Strongly solved by John Tromp's 8-ply database. Weakly solved for all board sizes where width plus height is at most 15. Drafts. English. This 8x8 variant of Drafts was weakly solved on April 29, 2007 by the team of Jonathan Schaefer, known for Chinook, the World Man-Machine Checkers champion. From the standard starting position, both players can guarantee a draw with perfect play. Checkers is the largest game that has been solved to date, with a search space of 5 times 1020. The number of calculations involved was 1014, which were done over a period of 18 years. The process involved from 200 desktop computers at its peak down to around 50. Fanarona. Weakly solved by Martin Schad. The game is a draw. Frigomoku. Solved by Victor Alice. First player can force a win without opening rules. Ghost. Solved by Alan Frank using the official Scrabble Player's Dictionary in 1987. Hex. A strategy stealing argument will show that all square board sizes cannot be lost by the first player. Combined with the proof of the impossibility of a draw, this shows that the game is ultra-weak solved as a first-player win. Strongly solved by several computers for board sizes up to 6x6. Jing Yang has demonstrated a winning strategy for board sizes 7x7, 8x8 and 9x9. A winning strategy for hex with swapping is known for the 7x7 board. Strongly solving hex on an n-times-n board is unlikely as the problem has been shown to be PSPACE complete. If hex is played on an n-times-n+1 board, then the player who has the shorter distance to connect can always win by a simple pairing strategy, even with the disadvantage of playing second. A weak solution is known for all opening moves on the 8x8 board. Hexapawn Kala. Most variants solved by Jeffrey Irving, Jeroen Donkers and Josie Whitewijic except Kala. The variant was solved by Anders Carstensen. Strong first-player advantage was proven in most cases. Mark Rawlings, of Gaithersburg, MD, has quantified the magnitude of the first-player win in the variant. After creation of 39 gigabytes of endgame databases, searches totaling 106 days of CPU time and over 55 trillion nodes, it was proven that, with perfect play, the first player wins by 2. Note that all these results refer to the empty pit capture variant and therefore are of very limited interest for the standard game. Analysis of the standard raw game has now been posted for Kala, which is a win by 8 for the first player, and Kala, which is a win by 10 for the first player. Analysis of Kala with the standard rules is ongoing. However, it has been proven that it is a win by at least 4 for the first player. L game easily solvable. Either player can force the game into a draw. Maharaja and the Sepoys. This asymmetrical game is a win for the Sepoys player with correct play. Nim strongly solved. 9 Men's Morris solved by Ralph Gasser. Either player can force the game into a draw. Ovalu weakly solved by humans but proven by computers. Panky strongly solved by Jason Doucette. The game is a draw. There are only 2 unique first moves if you discard mirror positions. One forces the draw, and the other gives the opponent a forced win in 15. Pentago strongly solved. The first player wins. Pentaminos weakly solved by H. K. Orman. It is a win for the first player. Corto solved by Luke Goosens. 2 perfect players will always draw. Cubic weakly solved by Oren Patashnik and Victor Alice. The first player wins. Rendu-like game without opening rules involved claim to be solved by Janos Wagner and Istvan Varag. A first player win. Sim weakly solved. Win for the second player. Tico solved by Guy Steele. Depending on the variant, either a first player win or a draw. 3 Men's Morris trivially solvable. Either player can force the game into a draw. 3 Musketeers strongly solved by Johannes Lair in 2009. It is a win for the blue pieces. Tic-tac-toe trivially solvable. Either player can force the game into a draw. Tigers and Goats weakly solved by Eugene Lim. The game is a draw. Partially solved games. Chessfully solving chess remains elusive, and it is speculated that the complexity of the game may preclude it in ever being solved. Through retrograde computer analysis, endgame table bases have been found for all 3 to 6 piece, and Sim 7 piece endgames, counting the 2 kings as pieces. Some variants of chess on a smaller board with reduced numbers of pieces have been solved. Some other popular variants have also been solved. For example, a weak solution to Maharaja and the Sepoys is an easily memorable series of moves that guarantees victory to the Sepoys player. Drafts. All positions with 2 through 7 pieces were solved, as well as positions with 4 times 4 and 5 times 3 pieces where each side had 1 king or fewer. Positions with 5 men versus 4 men, positions with 5 men versus 3 men and 1 king, and positions with 4 men and 1 king versus 4 men. The game was solved in 2007 by Ed Gilbert of the United States. Computer analysis showed that it was highly likely to end in a draw if both players played perfectly. Go. The 5x5 board is weakly solved for all opening moves. Humans usually play on a 19x19 board, which is over 145 orders of magnitude more complex than 7x7 MNK game. It is trivial to show that the second player can never win. See strategy stealing argument. Almost all cases have been solved weakly for K4. Some results are known for K equals 5. The games are drawn for K8. Reversi weakly solved on a 4x4 and 6x6 board as a second player win in July 1993 by Joel Feinstein. On an 8x8 board, it is mathematically unsolved, though computer analysis shows a likely draw. No strongly supposed estimates other than increased chances for the starting player on 10x10 and greater boards exist.